Okay, we're looking at the CFC solutions. So we had halons were used prior to CFCs. Now, both of these chemicals are used for their non-polar properties, so they're used as solvents, the propellant in aerosol cans, the refrigerants for air conditioning units. We were congratulating ourselves on the fact that they were stable, so they didn't break down in the environment, and this was their downfall with respect to the atmosphere. Because of their stability, CFCs can diffuse from the troposphere, where we are, where they're being used, up into the stratosphere, and we know the series of reactions that releases a chlorine free radical that destroys the ozone being good in the stratosphere because it protects us from harmful UV light. So this was a man-made chemical. Prior to its use, we had an even worse chemical called halons in use, and because they're man-made, we now need to come up with a way of solving this problem that we've created. One of them is the HCFCs. Notice that it now has a carbon-hydrogen bond in there, which is a deliberate insertion because the carbon-hydrogen bond is a weaker bond. It is going to, once the solvent's been used and escapes into the atmosphere, it will be acted upon in the troposphere and be decomposed, so it's not going to stay around to diffuse into the stratosphere and be a problem to the ozone layer. So that's one solution. An even better solution would be to remove the chlorine out of the molecule altogether, which creates a HFC, because we know it's the generation of the chlorine free radical that does the damage. Now, just recapping what each of those molecules are: the halon, carbon, chlorine, fluorine and bromine in them. CFCs, C standing for carbon, F for fluorine, and the other C is for the chlorine. HCFCs has got the hydrogen in it as well as the carbon, chlorine and fluorine, and HFCs have got the chlorine removed. Now, the ozone depletion potential is a number that gives us an idea of the destructive power of these molecules. The ozone depletion potential for halon is 10, compared to CFC's value of around 1. So halons are 10 times more destructive than CFCs. Now, how good has our first solution been of putting in that weaker carbon-hydrogen bond? The ozone depletion potential has gone from around 1 to 0.02. So it's a factor of 100, it's improved. Now, the ozone depletion potential of HFCs, where you do not have the chlorine free radical at all, is potentially 0, but we really can't say for certain because it was decades before we realised that CFCs were a problem. So we're hoping that the problem is totally removed by having the introduction of HFCs without the chlorine free at all. Now we need to know, so the solutions, bromine's really bad, putting the CH bond in is improving things, and removing the chlorine totally should be the best solution. So we need to know a little more detail about the last two. So to realise that this change is introducing this bond, which is weaker, so that it won't survive and go to the stratosphere and attack the ozone molecules, and the transition from this molecule to this one, HCFCs to HFCs, we're removing the chlorine altogether, knowing that that's the part of the reaction, the main part of the reaction that destroys the ozone molecules. So hopefully the problem's been addressed totally. This CFC solution is to address the dot point 4.3.3 in the syllabus, talking about replacements and evaluating their effectiveness as replacements for CFCs. The effectiveness is addressed with those ozone depletion potential numbers. Right, hope this has been useful.